Hello everyone, and welcome to today's lecture on strength of materials, specifically focusing on the method of sections. This is a fundamental technique used in analyzing structures to determine internal forces and moments, which is critical for ensuring that materials can handle the applied loads in engineering applications. Whether you're designing bridges, buildings, or any mechanical component, the method of sections will be a tool you often use. Let's get started by discussing the theory behind this method, and then we'll dive into the step-by-step process of how to apply it. Understanding static equilibrium. We begin by considering a body, denoted as est, in static equilibrium. This means the body is not accelerating or rotating, and all forces acting on it balance each other out. These forces are denoted as F1, F2, F3, all dots Fn, as you can see in figure 1.6a. But here's an important point. Even if the body is in motion, perhaps accelerating, we can still treat it as being in static equilibrium for a specific moment in time by applying what we call fictitious inertia forces. These reversed effective forces act through the mass center of the body. This method of simplifying a dynamic problem into a static one is referred to as D'Alembert's principle. For example, if the body is not just moving in a straight line but is also rotating, we need to apply reversed effective couples to maintain static equilibrium. Cutting the body, method of sections. Now let's break the body into two parts. Imagine a plane labeled as MN cutting the body into two sections. And part 2. This hypothetical plane intersects the lines of forces that represent the interaction between molecules situated on both sides of the cut, as shown in figure 1.6b. By cutting the body into two parts, we isolate the internal forces between them. These forces are labeled as A1 and A2, corresponding to part 1 and part 2 respectively. Since these two parts are no longer connected, the internal forces acting between them must now be treated as external forces. According to the principle of action and reaction, the forces on A1 and A2 are equal in magnitude but opposite in direction. Thus, the system of forces on either A1 or A2 represents the internal forces of the material. Equilibrium of forces and moments. Once we've separated the two sections, we analyze the forces and moments acting on them. For example, the system of forces on A1 can be reduced to a force, Fr, and a couple, Mr, acting at a specific point. Let's call it O. At the same time, the forces acting on A2 must balance these forces. The force on A2 is represented by -Fr and -Mr at the corresponding point O in part 2. Remember, O and O are the same physical point where the forces interact. Now let's talk about the equilibrium equations for both parts of the body. For part 1, we have sum Fn plus Fr equals 0, sum Mn plus Mr. For part 2, the equations are similar but with opposite signs. Fn minus Fr equals 0, sum Mn minus Mr equals 0. The sum of the forces and moments acting on both parts of the body must be 0 because the entire body is in static equilibrium. The stress resultants. Now, let's introduce the concept of stress resultants, which are the internal forces and moments distributed across the section. These resultants are expressed in terms of Cartesian coordinates. For example, the resultant force Fr and moment Mr acting on a section can be written vectorially as Fr Fxx high plus Fxy hat j plus Fxz hat k, Mr equals Mxx hat I plus Mxy plus Mxz hat k. Here, each subscript corresponds to the direction in which the force or moment acts. For example, Fxx is the component of force in the x direction, and Mxx is the twisting moment about the x-axis. Internal force components. Let's break these components down a little more. The 6 internal force factors that we'll be dealing with are 1. Ffxx, the normal force which acts perpendicular to the section. If this force pulls away from the section, it's tensile, and if it pushes towards the section, it's compressive. 2. Fxy and Fxz, these are tangential forces, or shear forces. They act parallel to the section, causing sliding between the sections. This is the twisting moment, which causes torsion along the bar. 4. MXY and MXZ. These are bending moments that cause the bar to bend along the Y and Z axes, respectively. Modes of load transmission. When analyzing any material or structure, it's important to understand the four basic modes of load transmission. 1. Tension or compression, forces that elongate or shorten the body. 2. Shear, forces that slide one part of the material past the other. 3. Torsion, forces that twist the material. 4. Bending, forces that cause the material to bend along its length. In many cases, a combination of these forces may be acting on the body at the same time. Steps in the method of sections. To conclude, let's summarize the steps in applying the method of sections. 1. Cut the bar using a hypothetical plane. 2. Remove one portion of the bar, either to the left or right of the section. 3. Apply forces and moments at the centroid of the section to balance the external forces acting on the remaining portion. 4. Solve the equations of equilibrium to determine the internal forces and moments. Method of sections. We consider a body S in static equilibrium subjected to a set of external forces, F1, Vf2, Vec F3, Vec Fn, as shown in Fig 1.6a. Even if the body is actually not in static equilibrium, for instance, if it is in motion having an acceleration, we can treat it as being in static equilibrium for a particular moment, provided we apply the fictitious inertia forces, also called reversed effective forces, as external forces acting through the mass center of the body at the given instant. This method of reduction of a problem of dynamics to that of statics is called the D'Albert's principle. Obviously, if the body is not only in translatory motion but also undergoes rotation, we would also need to apply reversed effective couple to bring about static equilibrium. We now imagine a plane MN through the body, cutting it into two parts I and II. This hypothetical plane must also intersect the lines of forces of interaction between molecules situated on the two sides of the interface, A, common surface of the two parts. Our next step is to imagine that the two parts of the body have been separated. We distinguish the two sides of the interface by A1 and A2, belonging to Part 1 and Part 2, respectively, as shown in Fig 1.6b. Since the two parts are no longer connected, it is necessary to replace the action of molecules A1 on the molecules A2 by a system of forces acting on A2, the section of Part 2. Similarly, there is a system of forces acting on A1, the section of Part 1. According to the principle of action and reaction, the system of forces on A1 is reciprocal, i.e., equal in magnitude, opposite in direction, and having the same line of action to the system of forces on us and A2. Thus, the system of forces on either A1 or A2 represents the internal forces, though they have been converted into external forces relative to Part 1 or Part 2 by the method of section. Following our basic assumption I, Art 1.3, the internal forces are continuously distributed over the surface of the section. In general, their distribution is rather complex. However, they must be so distributed as to satisfy the equations of equilibrium for Part 1 and Part 2 separately. Since the whole body is in equilibrium, any part of it must also be in equilibrium. The system of forces on A1 can be reduced to a force Vec Fr and a couple Vec Mr at any point in the section, say O. Then the resultant of the forces on A2 must be minus Vec Fr and minus Vec Mr. At the corresponding point O in the section A2, see Fig 1.6c. Remember that O and OPOW are the same point physically. The equations of equilibrium for the two parts can be expressed as follows. Part 1, sum Vec Fn core I plus Vec Fr equals 0, 1.2, sum Vec Mn I plus Mr equals 0. Part 2, sum Vec Fn 2, 1.3 Vec Mn 2 Vec Mr equals 0, where Vec Fn core I and sum like 2 are the vector sums of the external forces acting on part 1 and part 2, respectively. Similarly, sum ni and infima 2 are the vector sums of the moments of the external forces about the point O, acting on part 1 and part 2, respectively. Also, since the whole body is in equilibrium, we have vec Fn equals sum vec Fn plus sum vec Fn2 equals 0, tie 1.4, vec Mn equals sum vec Ni plus sum vec Mn2 equals 0. Consequently, we find that EQ is 1.2 and 1.3 are identical. Any one of these is sufficient to determine the resultant of internal forces, also called stress resultant at any section, provided we know the external forces. It is also obvious that we need to consider the FBD of only one portion of the body, either to the left or to the right of the section, for the evaluation of the stress resultant. The resultants vec FR and vec MR are generally expressed in terms of their components with respect to a system of Cartesian coordinate axes. We will be dealing mostly with prismatic bars. We have shown in Fig 1.7 the components of VEF-R and VEC-MR at an arbitrary cross-section of such a bar with respect to a set of axes XYZ, so chosen that x-axis is in the direction of the normal to the section. Conventionally, the resultants are found at the centroid of the section. A double subscript notation has been used to designate the components. The first subscript denotes the direction of the outer normal to the section and thereby specifies the section, while the second subscript indicates the direction of the component. Thus, F for XX denotes the component of VFR on X section in X direction. FXY is the component acting on X section in Y direction, and so on. VFR and VEC-MR on the given section can be written vectorially as FR equals FXX hat I plus FXY hat J plus FXZ hat K. VMR XX hat I plus MXY hat Z cat T. The six components, namely FXX, FXY, ZX, MXX, MXY, and MZ are called the internal force factors. As for the sign convention, we shall follow the rules given in the next paragraph. A component acting on a cross-sectional area whose outer normal points in the positive direction of any coordinate axis will be taken as positive if the component itself also points in the positive direction of any coordinate axis. A component is also positive if both the area vector, represented by the outer normal, and the component point in the negative direction of the same or different coordinate axes. If, however, the area vector and the component are not directed simultaneously in either positive or negative coordinate directions, the component is negative. An inspection of the components shown in Fig 1.7 will show that they are all positive. Each of the six components on a section reflects a different manner in which the external forces are transmitted across the section and is, therefore, given a special name as detailed below. I, the component, FFFXX, normal to the section, is called the normal force. It is tensile if it acts away from the section and compressive if acting towards the section. The tensile force tends to elongate the bar, whereas a compressive force tends to shorten it. If only normal force occurs at the cross sections of the bar along its length, the bar is said to be in pure tension or compression, depending upon the sense of the normal force. E, FXY, and FFZX are the tangential components. They have a tendency to slide or shear the bar to one side of the section past the other. They are, therefore, called shearing forces. The two components may be combined to get the resultant shearing force at a given section. The moment component MXX is the moment about the axis normal to the section, and it tends to twist the bar. It is called twisting moment. If only this moment occurs at the cross sections of a bar along its length, the bar is said to be under pure torsion. IV, the moment components M, XY, and MZ are the moments about the transverse axes Y and Z of the section, and they have a tendency to bend the bar about these axes. Thus they are called bending moments. If the loading is such that only bending moment is present on the cross sections, the bending is said to be pure, And if it is accompanied by shear forces 2, the bending is called transverse. Thus, we have seen that there are 4 basic modes of load transmission through a member, namely A, tension or compression, B, shear, C, torsion, and D, bending. The transmission may also take place by a combination of these basic modes. In view of the importance of method of sections, we summarize below the steps taken in the method to determine the internal force factors. The steps are A, to cut the bar by a hypothetical plane, B, to remove one portion of the bar either to the left or to the right of the section, C, to apply at the centroid of the section components of force and moment capable of balancing the external forces acting on the remaining portion of the bar, and D, to finally determine the components of the force and moment from the equations of equilibrium for the system in C above. And that concludes our discussion on the method of sections. Understanding these internal forces and how they interact within a structure is essential for analyzing and designing safe and efficient systems in engineering. I encourage you all to practice with examples and apply these principles to real-world scenarios. Thank you for watching, and see you in the next lecture.